Welcome to the Explainer. Today, we're diving right into grade 8 geometry. So imagine you're an architect or maybe an engineer, and you need to build an exact replica of a triangular structure. You can't just guess the dimensions, right? You need a geometric blueprint that absolutely guarantees your new shape will match the original perfectly. But here's the real question. How much information do you actually need to build that exact replica? Do you have to know every single angle and every single side length? Well, as you'll see, mathematics actually gives us some pretty brilliant shortcuts. Let's dive into this and discover how we can build exact replicas using minimal information. Here's our map for today's journey. First, we'll start by defining congruent triangles. Second, we'll check out the SSS, or side-side-side rule. Third, the SAS, side-angle-side rule. Fourth, we're going to look at the SSA ambiguity. And finally, we'll wrap things up with a recap and a transfer question.
All right, part 1, defining congruent triangles.
So, the formal definition from our geometry standards states that two plane or solid figures are congruent if one can be obtained from the other by rigid motion. Think of rigid motion like physically picking up a solid wooden puzzle piece. You can slide it across the table, that's what we call a translation. You can spin it around, that's a rotation, or you can flip it over entirely, a reflection. The absolutely crucial part here is that no matter how you move it, you are never stretching it, shrinking it, or bending it. The size and the internal angles remain completely locked and totally unchanged. Now here's the kicker. Congruence requires what we call explicit correspondence. You can't just eyeball two triangles and say, yeah, they look about the same. You actually have to prove that they match up perfectly. Every specific side on the first triangle must have a perfect matching partner of the exact same length on the second triangle. And it's the exact same deal for the angles. Every specific angle has to match a corresponding angle of the exact same measure. We're talking about a strict, exact, part-to-part alignment here. Moving right along to part 2, the SSS, or side-side-side rule. Picture this for a second. Imagine you've got some basic geometry tools in front of you. Maybe it's some digital software, or just literal wooden sticks of very specific lengths. Step 1, you place your points to define the vertices. Step 2, you lock in 3 segments of specific lengths. Let's say a 3-inch stick, a 4-inch stick, and a 5-inch stick. Step 3, you close the polygon by snapping those ends together, and this perfectly illustrates the SSS rule. If you use those 3 exact lengths, there is literally only one unique triangle you can possibly build. Sure, you can rotate it or flip it, but the actual shape of the triangle is permanently forced by those 3 fixed side lengths. It's locked in. Okay, it's time for a quick pause check to make sure we're on the same page. Think about this. If 2 triangles have the exact same perimeter, meaning, the total distance around the outside is identical, are they guaranteed to be congruent by the SSS rule? Take a second and think about it. The answer? A massive, definitive no. And here's exactly why. Side lengths must correspond exactly, part to part. Just adding up to the same total perimeter is definitely not enough. Let me give you an example. A triangle with sides measuring 4, 4, and 4 obviously has a perimeter of 12. But a completely different triangle with sides measuring 3, 4, and 5 also has a perimeter of 12. Same perimeter, totally, completely different shapes. So remember, SSS requires the individual corresponding sides to match up exactly. All right, let's hit part 3, the SAS, or side-angle-side rule. Now, to actually use the SAS rule, we absolutely must understand the difference between an included angle and a non-included angle. It's super important. An included angle is perfectly wedged right between 2 known sides. It connects them together. Sort of think of it like the corner of a door frame. On the flip side, a non-included angle sits completely outside those 2 known sides. It's not the hinge connecting them. So for the side-angle-side rule to actually work, our angle must be that included one. So here is how the SAS correspondence rule breaks down in practice. Imagine building this out. You lock in side 1, then you set a very specific angle. That's your included angle hinge, and you lock it tight. Finally, you attach side 2 at its specific length. Now look at what happens to the remaining gap. Because those 2 sides and the angle wedged between them are rigid and locked, the third unmeasured side naturally gets forced into a specific unavoidable length just to close the triangle. It has no choice. If those 3 SAS components match another triangle exactly, the 2 entire triangles must be congruent. Time for another pause check. We just laid out the structure for SAS. So ask yourself, does that known angle absolutely have to be between the 2 corresponding sides for this rule to guarantee congruence? Yes, 100%. It absolutely must be. It has to be the included angle because that angle acts as your crucial structural hinge. If you move that known angle somewhere else, you completely lose control of the hinge. And honestly, the entire structure just falls apart. Which brings us nicely to part 4, the SSA ambiguity. We're entering the danger zone here. Our mathematical standards explicitly call out the issue with this particular rule breaker. They state, these laws yield 2 possible solutions in the ambiguous case, illustrating that side-side angle is not a congruence criterion. Let that sink in for a second. Side-side angle, or SSA, mathematically fails to guarantee a single, unique congruent triangle. So why exactly does SSA fail? Well, in a side-side angle scenario, your known angle is not wedged between your 2 known sides. It's a non-included angle. Because that second known side isn't locked down by an included angle hinge, it's completely unanchored at one end. It literally acts like a swinging pendulum. You can swing that side inward to form a short, wide, obtuse triangle, or you can swing it outward to form a taller, acute triangle. Both of those triangles would have the exact same side, and angle measurements, but they are 2 completely different shapes. Hence, it's totally ambiguous, and we absolutely cannot use it as a rule for congruence. All right, part 5. Let's bring it all together with a recap and transfer. Let's do a quick recap of what we've covered. First up, true congruence is all about rigid motion, sliding, turning, and flipping, while maintaining that exact explicit correspondence between parts. Second, the SSS criterion guarantees congruence by locking down all 3 matching side lengths, which forces a single, unique shape. Third, SAS guarantees congruence by locking 2 sides with an included angle acting as a rigid hinge. And lastly, remember the danger zone, SSA fails as a criterion because that unanchored, not included side swings back and forth, creating 2 entirely different possible shapes. Before we wrap up, I want to leave you with a final thought to really test how well you can transfer this knowledge out of the classroom and into the real physical world. Imagine you're a surveyor, and you're standing on the bank of a raging river. You need to know the exact distance across it, but you absolutely cannot cross it. It's just not happening. How could you use your brand new knowledge of SSS or SAS congruence to set up an identical congruent triangle on dry land, which would allow you to indirectly measure the river's width? Think about how you'd lock in those angles and sides on your side of the riverbank. Good luck figuring it out, and keep looking for the geometry in the world around you.